Hello everyone and welcome to Physics and Dynamics tutorials. In this tutorial we will solve a problem related to Newton's second law and motion of two boxes that are connected by a cord and a pulley. This is the classical problem that in a more complex form appears in a number of engineering and aerospace applications. Consequently, it is very important to know how to accurately solve this problem. The problem solved in this video tutorial is also very important for students who want to master basic and advanced physics topics, as well as for students who want to prepare themselves for the Advanced Placement Physics exam, that is, for the AP Physics exam. Furthermore, by learning how to solve this problem and by watching this video tutorial, a student can obtain a deep and intuitive understanding of mathematics, physics, and algebra. Before I start with explanations, I have to mention that it took me a significant amount of time, energy and planning to create this completely free video tutorial, as well as more than 300 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. First, we need to carefully read the problem statement. Two boxes, here are the boxes, are connected by a cord and a pulley. Cord and a pulley. We assume that the mass of the pulley and the cord can be neglected, as well as the friction between the rope and the pulley. We assume that the cord is not elastic. We assume that the masses of two boxes are given. M1 is equal to 5 kg and M2 is equal to 10 kg. Box 1 slides over the surface with the coefficient of kinetic friction mu is equal 0.25. Determine number 1, acceleration of boxes. Number 2, tension force in the cord. To solve this problem, we first need to construct free body diagrams of the box 1 and the box 2. Let us construct the free body diagram of the box 1. Here's the box 1. And let's analyze the forces acting on this box. Obviously, we have the weight of the box. M1g, where g is the gravitational acceleration. Then, we obviously have the reaction force N. This is the force that the surface is exerting on the box. And this is the normal component of the reaction force. Then we have tension force in the cord. Here's the tension force, T. Then we have the friction force. Let us assume that the box will move in this direction. This means that the friction force will act in the opposite direction. Here's the friction force, F mu. And finally, let us sketch the acceleration vector of the box 1. Here's the acceleration vector, and we will denote this acceleration vector by A1. Next, let us construct the free body diagram of the second box. Here's the second box. And let's analyze the forces acting on this box. Obviously, we have the weight of the box 2, that is, we have M2 times G. In addition, we also have the tension force in the cord, and the tension force acts in this direction. This is the force that the cord is exerting on the box number 2. And obviously, the intensity of this force is equal to the intensity of this force. And I will denote this force as T. However, I will not use the same notation as here, since these two vectors are actually different. One acts in this direction, one acts in this direction. However, their intensities are the same. And consequently, I will simply add here a star. That is, the intensity of T is equal to the intensity of T star. And in addition, we need to add the acceleration vector. The acceleration of box number 2 is in this direction, and it's denoted by A2. We will later see that the intensity of A1 is actually equal to the intensity of A2. The next step is to apply Newton's second law. To apply Newton's second law, we need to introduce the coordinate system. This is x1 and this is y1 for the free body diagram 1. Let us write Newton's second law. Mass 1 times the acceleration of box 1 is equal to the sum of all the forces acting on box 1. Let's see what do we have here. We have obviously F mu, then we have N, then we have M1G, that is the weight of the box, and finally we have T. And note over here that this is a vector equation. That's why I have plus signs over here. Later on, I will project this vector equation onto axes x1 and y1 to obtain scalar equations. Perfect. From this equation, we obtain the following. Namely, we can project this equation onto the axis y1, and as the result we obtain 0 is equal to, let's see, n minus m1g. I have 0 over here since the acceleration doesn't have the component in the vertical direction, and consequently the projection of the acceleration on the y1 axis is 0. And from this equation, obviously I obtain that normal force is m1g. Perfect. Next, we need to project this equation on the x1 axis. As the result, we obtain m1 times a1 is equal to, let's see, F mu projection is minus F mu. Then we have plus T. And do we have something else? Let's see. No, that's it. Now, we know that F mu is actually equal to mu times n. That is the coefficient of kinematic friction times the normal force. And by using this equation, we can actually figure out that F mu is mu times m1g. Now, by substituting this expression in this equation and writing the equation over here, we obtain m1 times a1 is actually equal to T minus mu m1g. Okay, now let's analyze this problem. Obviously, the acceleration intensity of this box is equal to the acceleration intensity of this box. That is, we have that, as I wrote over here, and I will repeat it again, A1 intensity is equal to A2 intensity. Next, we will introduce the following notation. We will introduce the acceleration A, and the acceleration A is actually equal to A1, which is equal to A2. By using this fact, we can write this equation like this. M1 times A is equal to T minus mu M1G. Perfect. This is our first equation. In this equation, we don't know A and we don't know T. Consequently, we need to obtain an additional equation in order to solve this problem. And this additional equation will be found by applying Newton's second law to this free body diagram. Over here, I'll draw a red line, and below this line, I will apply Newton's second law to this problem. Let's apply Newton's second law. What do we see over here? We have that m2 times a2 as a vector is equal to the sum of all the forces acting on the box 2. The forces are obviously weight m2g plus t star. Okay, now let us introduce the coordinate system over here. Again, I will introduce the coordinate system like this. This will be y2 axis and this will be x2 axis. Perfect. And obviously this equation only has projections on the y2 axis, and the projections are, let's write, m2a, however, a2, however with the minus sign, since the acceleration goes downwards, so we have minus this part over here, and let's see what we have over here. We have minus m2g, and what do we see over here? The intensity of T star is obviously equal to the intensity of T. And we will simply denote this intensity by T. By using this fact, the projection of this tension force T star will be simply be T. Again, since the cord is not elastic, the tension force is unique. That is, better to say, the intensity of the tension force is unique. However, the tension force, for example, has this direction if it acts on box 1, or it has this direction if it acts on the box 2. However, the intensity is the same, and we are using this fact. Okay, next, we will use this equation to write this equation as follows. Minus m2a is equal to, let's write, T minus m2g. By multiplying this equation with minus 1, we obtain the second equation. m2a is actually equal to, let's see, m2g minus t. And this is the second equation. And this was the first equation over here. We will use these two equations to compute A and T. To make this video tutorial as clear as possible, over here I've wrote again these two equations. We need to solve this system of equations for A and T. How to do that? From the first equation, we can express T as T is equal to m1a plus mu m1g. And then we can substitute this expression in this equation. As the result, we obtain m2a is equal to m2g minus m1a minus mu m1g. Let us analyze this expression. We have m1a here and we have m2a here. Consequently, we can write m1a by moving this part on the left-hand side plus m2a is actually equal to m2g minus mu m1g. Then we can write m1 plus m2 multiplying a is equal to, let's see, we can take g out, and inside we have m2 minus mu m1. Perfect. And finally, the acceleration a is equal to g multiplying this expression or this fraction. In the denominator we have m1 plus m2, and in the numerator we have m2 minus mu m1. By substituting the values we obtain, this is equal to 9.81 multiplying what? Multiplying, let's see, m2 is 10 minus mu is 0.25, multiplying what? Multiplying m1, and m1 is 5. And in the denominator we have simply 10 plus 5. I will use Python to compute this expression. Here it is. Here is my A. If I substitute m1, m2, g, and mu, and if I code the expression for A, I will obtain as the result A is equal to 5.7225. 5.7225, and the unit is obviously meter over second square. Perfect. How about the tension force? Once we determine the acceleration, from this equation we can determine the tension force. The tension force is simply equal to m1 times A plus mu multiplying m1g. And let's see the result. We have m1 is 5, multiplying the acceleration 5.7225 plus 0.25, multiplying m1 is 5, multiplying 9.81. And as the result we obtain the following. Let's see. We obtain that T is equal to 40.875 newtons. So it's 40.875 newtons. And that's the solution of the problem. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.